Welcome everybody. So today we're going to talk about solubility and specifically something called the solubility product constant. And this is for salts that don't dissolve very well. And I know that in the past you've been told about insoluble salts. And when people think about insoluble salts, they think about salts that do not dissolve. And so you sort of have this picture in your mind about how, nothing gets dissolved at all. But even with things that are considered insoluble, there's still some sparing bits that are dissolved within the liquid. For example, something like AgCl. So you might have learned from one of those solubility charts that AgCl does not dissolve in water. Well, it does dissolve, just very, very little of it dissolves. And we can actually calculate that with a value known as Ksp. If you're soluble, that means that a lot of salt dissolves, and normally this would be in grams per milliliter amounts. Whereas here, when we talk about something that is AgCl, we might be doing grams per liter or even milligrams per liter, depending on how insoluble the salt is. And you'll see differences in what that looks like. So let's talk about these two terms, saturated versus unsaturated. And this chapter I do as part of equilibrium because saturated can be thought of as a state of dynamic equilibrium. And what I mean by that is that you have these equal rates going on. The equal rates that are occurring would be the crystallization or precipitation and the dissolving. And something important about saturation that you need to keep in mind is that the only thing that can really affect it, especially for we're doing solids, the only thing that can really affect it is temperature. If we, add more, solute and try and dissolve it, if it's already saturated, no more will dissolve. If we try and evaporate some of the water, and we'll talk about that down here, more will precipitate out, but the total concentration will not change. If we try and increase the pressure, if it's a solid dissolved in the liquid, there won't be a change either. However, if you have a gas in a liquid, then pressure can affect the solubility. And they'll ask you sometimes on the AP exam, you'll see the effect of evaporation on saturation. And so let's say that you had, like a saturated solution of AgCl, and the volume was 1 liter. And let's say that the concentration of the AgCl in the solution was, 0.3, or let's do 3 times 10 to the negative 5 molar. 3 times 10 to the negative 5 molar of Ag plus and Cl minus. So now if I evaporate this and I make this 0.5 liters, well, the molarity is still the same. It's still 3 times 10 to the 5 molar Ag plus and Cl minus. Has the amount that's dissolved changed? The moles have changed, and we could calculate the moles in each of these, and you'd see that the moles do change, but the molarity, the concentration, the moles per liter, that does not change. Okay, so let's get right to it. Let's talk about the Ksp problems that you're going to see and what Qsp is as well. So, here's a typical salt that you might have learned about, lead sulfate, lead 2 sulfate, and it's an insoluble salt. It doesn't dissolve very well. And so we can show an equation for this where what would it look like if it did dissolve? It would form these two ions, lead plus 2 and SO4, 2 minus. And we could, look at this and say, well, how much of it dissolves? We need to do an experiment to kind of figure that out. Well, we can write a Ksp for this, an equilibrium expression, and it would look like this. We would have our Kc value. It would be equal to the products over the reactants. But if you remember that the solids, we don't include those in the equilibrium, and so that we cut out, and then we're left with just the products, hence the term solubility product. We have just the products. If we're not at equilibrium, if we're not saturated, then instead of K, we would have a Q value, just like in equilibrium. When you're not at equilibrium, you use the Q value, not the K value. So how does this look mathematically? Well, let's look at a problem and what it looks like mathematically. So here's the same salt, PbSO4. and they ask you what's the KSP for PbSO4, and they give you this concentration in grams per milliliter. And so the first thing I need to do is I need to make the concentration in molarity, because that's what gets plugged into the KSP. So I take the milligrams and it's in grams. I times it, it's per 1 milliliter. So I times it by 1,000 milliliters per liter. And then I change it from grams to moles. I times it by 1 over the molar mass. And I get this molarity right here. Now, I can write an equation for PbSO4, and I like to do that because it helps me to practice writing the equations for these things. Equations are always good to try and frame out what your ideas are. And so we have Pb plus 2, and that's an x. PbSO4, that's an x as well. It's kind of like an ice table, but not really. You could start with 0 and do plus x and then x, but I just kind of, write what it is in the final. We'll do some ice tables when they get a tiny bit more difficult. But we already know x because we know the molarity, and so we can just plug that into our KSP, multiply them out, and solve. And we'll get 1.96 times 10 to the negative 8th. So what I'd like you to do is I'd like you to try one of these down here. Here's PbF2. This one might be a little bit more challenging. I tell you what the solubility is. And when I give you something like this, here's the solubility, what you want to do is change it to molarity. And this molarity is going to be equal to your x value. But when you do this practice problem, not to leave you hanging out here, but find the molarity, that's the first thing. And then write a KSP. So write a KSP for this. Once you write the KSP for this particular salt, then show the equation too. Show the dissociation equation. You might even want to do that first. So write the dissociation equation, then the KSP. And then you can plug in the values. So then plug in values. This one isn't easy, I have to say, because you're going to have two different values because PB and your F are not going to be the same values. And this one is really only the value for the X. Now, I don't want to give too much away. I'd like you to try this on your own and see how you do with it. And let me know. And tomorrow in class, we're going to go through this, and we're going to actually try and do this one and see how you do with it. Okay, determining solubility from KSP. So now we're going the other way. We're given KSP, and we're asked to find what the molar solubility is. And so when they say solubility, they're talking about something called molar solubility, and that would be your X value. So how do I go about doing this one? Well, I write out my formula for my reactant. I show that it forms the ions, and this one will form just like PbF2. You might want to use this as an example to write out PbF2, and this would be 2OH minus. Now, I'm starting with 0 of each. Here, I'll set up an ice table, show you how that's done. And I have plus x and plus 2x, x and 2x. And so now when I go through and I try this one, if I write out my KSP is equal to Ca plus 2 times OH minus squared. If I put in my values for x, I know KSP, it's 6.5 times 10 to the negative 5th. That's equal to x for Ca, 2x all squared for OH minus. And this is where you have to be careful. 2x squared, it becomes 4x squared times x equals the same KSP. And then this can be all condensed into 4x cubed. And so now we can go ahead and we can solve for x. So first I would divide the value by 4. So I would take my 6.5. Let me just put this in, 6.5 times 10 to the negative 5th. And then I would divide it by 4. And then I would cube root that. And I would get that the molarity would be 0.025 molar. Now that's my value of x. If they asked you specifically, what's the value of OH minus, that's 2x, and you have to be careful and read really into it what they want you to do. Now, one last thing that I want to talk about is just the beginning of this slide here. I'm going to do common ion next time. But one thing I want to just touch upon with you is that, if you want to compare two salts to each other, something like, let's say, AgI and let's say, PbCl2. And I don't know their KSPs, but just to make one up, just to compare them, this is 1 times 10 to the negative 10th. And this KSP over here is like 1 times 10 to the negative 8th. And you want to compare these and say, yeah, well, this is more soluble, because it has a higher KSP. That's actually wrong. You can't do that. And why can't you do that? That's something that you really need to think about. Why can't I just compare the solubilities for these by looking at the KSP? Think about that one. Tomorrow we're going to discuss that in class. And then when I do the next video, I'll sort of touch upon what we discussed. And we'll talk about common ion and how it affects solubility. And we'll do some practice with those. And then we'll do pH on solubility, and then predicting if a precipitate will form or not. We'll do some of those problems as well. Again, this is just sort of like an addendum to acids and bases. It's a short chapter. There's just the calculations that go along with it. All right, thanks so much for watching.